Nice to see so many people here. Maybe, Chris, another suggestion for asking question is raising your hand in Zoom if you don't want to type out your question. I think that works also quite well. Yes, so we will have another, today, 2 hours of lecture and another 2 hours of lecture with me on Wednesday, and then there will be 2 hours with Matteo on Friday. What I will cover in this course, roughly, and in that order, first we will talk really about, well, literally the background of quantum field theory and curved spacetime, namely about curved spacetimes. Then we will talk a bit about the Klein-Gordon equation, because this is the example that we will work with. We will work with the scalar field. So the Klein-Gordon equation is an important ingredient, or the fundamental ingredient. Then we will talk about algebraic quantum field theory, and for this we also need some concepts and results from theory of star algebras. Then, after we have discussed some general aspects of the quantization of the scalar field, we will go on to some special cases. First, I want to discuss with you quantum field theory in ultrastatic spacetimes, then quantum field theory in the Rindler wedge, and this will then include the Unruh effect, and we will see how much more we can do and continue maybe with some other topics. And there will eventually be lecture notes. They are not entirely ready, although essentially typed up, and we will make them available as soon as possible. So let's start immediately then with the first topic. Let's talk a bit about causality, and the big aim of this section will be to introduce the concept of globally hyperbolic spacetimes. The reason is that globally hyperbolic spacetimes in the end allow us to formulate nice Cauchy problems for the typically generally hyperbolic operators, and specifically for us for the Klein-Gordon equation. And starting with the very basic, let's first define what a Lorentzian manifold is, or what I roughly understand by this. This is a pair consisting of a manifold and a metric. More concretely, a Lorentzian metric, and in the signature that I work with, that means a metric of signature minus plus plus plus. Yes, so different than from Riemannian geometry. We have here not a positive metric, but this metric now allows us to distinguish at each point vectors according to the sign of, well, the norm defined by the metric. So if the norm is positive, the vector is called space-like. If it's 0, it's called light-like. Time-like if it's negative, and causal if it's either light-like or time-like. You can see that schematically in this picture here. More accurately, I should have drawn a double cone, but then it would have been more difficult to see much in this picture. So there's another side of this cone down there. And the space-like vectors, they are, from the physical point of view, maybe, let's say, less interesting. But the world lines of observers, they have time-like tangents. Light travels along curves which have light-like tangents. So for physical objects, we are interested in causal curves. And let's, for this reason, then put all the causal vectors in one set. And if we have a connected Lorentzian manifold, then it can happen, and this is the desirable case that we want, that this set separates in two components. And this is what we call then a time-orientable Lorentzian manifold. And if we can separate these two, we can give each component a name. And this is then the choice of time orientation. We call one direction the future, causal future, and the other direction the causal past. We will denote this J plus or J minus. And this is now what I call a space-time. For a spacetime, I want a connected, time-oriented Lorentzian manifold. The connected part makes the definition above easier, but really, if it was not connected, then as far as the physics certainly is concerned, I could just treat each component as a spacetime in its own right again. And so reducing to the connected case is no restriction for us. So we have a connected time-oriented Lorentzian manifold. Let's see what we can do with it. Let's suppose we have a curve on this spacetime. Yeah, so then if its tangents, all the tangents of this curve are causal future vectors, we say that this curve is future-directed causal. And then, if we have now 2 points, say P, first one point, P, then another point, Q, will be in its causal future if I can draw a curve between the two, such that this is a future-directed causal curve. And all the points that can be reached by future-directed causal curves, these I will denote by J plus of P. And if I start not with one point, but with a whole set of points, then I denote the causal future of the whole set by the union of the causal future of all the points in that set. So here I drew an example. I have some strangely shaped set in the manifold, and then I essentially have the shadow into the future of that set. That's the set J plus N. And I can do the same thing to the past, and these sets are then not denoted with a plus, but with a minus, as written here. Let's do a bit interesting things with these sets J plus and J minus. We say that a subset of a spacetime is called causally convex if it is equal to the intersection of its own causal future and past. So here I have a good set which is causally convex and one which is not. Here I could pick 2 points and draw a causal curve which leaves the set. So this is not good for many purposes. Often we need to work with causally convex sets. If we pick 2 points in a causally convex set, there will always, all causal curves that connect these 2 points will lie inside the set. That's what this definition implies. And later on, we will also need the notion of a space-like compact set. That is a set which lies Well, imagine cutting it in the spatial direction. In each slice, it's compact. Then it's space-like compact. And a more slicing independent definition is the one I've given here. If you can find a compact set such that its shadow to the past and the future contains the set n, then we call the set n space-like compact. If we have now two sets, we can ask if they are causally disjoint. And that means that one set is not in the causal shadow of the other set. So here in the picture I drew, we see three sets. We see that the blue set is causally disjoint from the yellow set. Well, actually also causally disjoint from the red set. But the yellow and the red set, they are not causally disjoint. Meaning we can draw from the yellow set to the red set, we can find causal curves. But any curve from the yellow to the green, from the yellow to the blue set is space-like. And this already is enough for us to define what now a globally hyperbolic spacetime is. A globally hyperbolic spacetime is a spacetime that is causal, meaning that it contains no closed causal curves, and diamond compact, meaning that for every two pairs of points P and Q, if I take the causal future of one point and the causal past of the other point, then the intersection of the two sets will be compact. Yeah, so we always want a situation like on the picture on the right, not something strange. Actually, and this was only proven relatively recently, this causality condition is somewhat redundant in the interesting cases. So we will only be interested in spacetimes of dimension larger than 2. And we will, for other reasons, also only be interested in non-compact spacetimes. So really the important thing is this causal, this diamond compactness. There are many examples of globally hyperbolic spacetimes, but there's also important counterexamples. Any compact spacetime will not be globally hyperbolic. Compact spacetime necessarily always has closed causal curves. Especially, we already see this if only the time direction is compact, like in the second example, then we will have closed causal curves. Here, in the second example, these closed causal curves are simply curves which with constant x. They are just circling around. Other examples of spacetimes which are not globally hyperbolic are the spacetimes which have naked singularities. For example, we could take Minkowski spacetime, so just R4, and remove any time-like curve. This will not be globally hyperbolic anymore. Essentially, this means there will be some geodesics in the spacetime that must terminate at this time-like curve, and this is not good. This destroys diamond compactness in the end. Let's come to some examples. The first one is ultrastatic spacetimes, these are spacetimes which can be written as a product of some time direction, which is just the whole real line, and some spatial direction. And the metric is really simple. We have just minus dt squared plus some spatial metric. And the spatial metric does not depend on time. So this is what it means to be ultrastatic. It's as static as it can be. And if, in addition, we have that this the spatial part of this space-time is a complete Riemannian manifold, and I will explain this in more detail probably on Wednesday, meaning that all the geodesics that are inextendable, so as long as they can be made, well, if we take them, they are all isometric to R. This is one way to think about complete Riemannian manifolds. If you already have a globally hyperbolic spacetime, then you can make a conformal transformation of that spacetime, meaning you can multiply the metric with a positive function, and this will not change the causal structure of the spacetime. This will change length and curvature and so on, but not the causal structure. So global hyperbolicity is preserved under conformal transformation. And very important for us is the last example, because we will often look at embeddings of spacetimes in other spacetimes. If we already have a big spacetime, let's call it M, and now we take a causally convex open set of it. A nice causally convex open sets are always these type of diamonds. Then the restriction of that large spacetime to the small spacetime, if that small set is causally convex and open, will also be globally hyperbolic. We need often also some maps between globally hyperbolic manifolds. Not all of them are equally good for us. So suppose we have two globally hyperbolic spacetimes, and we embed one of these spacetimes into the other. We will say that such an embedding is admissible, nice, if the metric is preserved, yes, meaning that the push forward of the metric on the, the pullback of the spacetime on the second manifold is equal to the metric on the manifold N. Also, we want that the time orientation is preserved. I will not talk much about orientation, which you kind of want when you have want to talk about integration, say. But orientation should also be preserved. And importantly, again, and this fits together with what we had before as our important example of a globally hyperbolic manifold, we want that the image of this map in the bigger spacetime is causally convex. And we see in the picture here an example where this is not the case. Well, we could map our spacetime into the larger spacetime inside some diamond. That would be okay. But let's stretch this diamond, and let's assume this bigger spacetime is this cylinder, and let's wrap this diamond around the cylinder. Now we have created the situation where we can draw a causal curve from one part of that embedded set into the other. And this is something that we don't want. We lost the aspect that the image of the smaller space-time is again globally hyperbolic as a subset of M. Okay. And with this, we come now to the last few definitions that I want to make about causality and globally hyperbolic spacetimes. It's about splitting and foliating globally hyperbolic spacetimes. We want to solve initial value problems, Cauchy problems. For this, we need some way to specify initial data somewhere, like you're used to in physics or other Cauchy problems. And not any surface will do. What we need is a Cauchy surface, and a Cauchy surface is defined as a hypersurface which is intersected exactly once by every inextendable time-like curve. Essentially, this kind of means that the information that is transmitted is somehow transmitted one-to-one from each surface to the next, very vaguely. And the next theorem has for a very long time been kind of folk theorem, which everybody assumed to be true, but in its full glory and all properties was not shown till the early 2000s, if I remember correctly, by Bernal and Sanchez, is that any globally hyperbolic space-time is isometric to the manifold R times spatial manifold with a metric which can be written for some time coordinate as minus beta dt squared plus some metric on the spatial parts, but now different than in the ultrastatic case. This G sigma can depend on time. Yes. If it did not depend on time and also beta did not depend on time, then this would be called a standard static spacetime. Anyway, so the result says that mg is isometric to that spacetime where beta is a positive function and which is also smooth. And these metrics G, or these tensors G sigma, they can be restricted to sigma, and then you get a whole family indexed by T of Riemannian metrics on sigma. So you end up with, in the end, by a foliation of the space-time by smooth and space-like Cauchy surfaces, where each Cauchy surface is equipped with this metric G sigma T. Yes, so you can really have a very nice slicing of the space-time by smooth surfaces, as drawn in this picture. And this sets us up to now solve Cauchy problems in that space-time. So let's continue and look at the Klein-Gordon equation. Let's first make sure we are all on the same page of what I mean by the Klein-Gordon equation. By the Klein-Gordon equation, I mean some equation, some differential equation, partial second order, which is given by the metric and the covariant derivative. So we have really the D'Alembertian box given by minus the metric contracted with the covariant derivative, and we have some potential. Often we want this potential to be something special. Maybe we want it to be positive. Maybe we just take a mass. Just having a mass, this would be the conventional case, the standard Klein-Gordon equation that we know from Minkowski space. Now, standard Klein-Gordon equation for standard Q of t would just have a mass term. The obvious generalization of this to curved spacetime would allow also that we add some curvature term. This has the right dimension. There's no reason why we shouldn't add it. And we just don't know which one is the right one. So there's just some dimensionless parameter in front of it, this psi. A kind of preferred value of psi is either 0, which removes it altogether. This is called the minimal coupling, or 1/6, which is called the conformal coupling. If you ask me, the best value is 1/6. But why not? I mean, why not do general potential? At least the math allows us to do it. Yes. So with this, I call this operator of the D'Alembertian plus the potential K for Klein-Gordon. And the Klein-Gordon equation is then simply this operator applied to a scalar function. And on the right-hand side, we either have 0 or maybe we have some source term. And we want to solve this equation on a globally hyperbolic manifold. And for this reason, I will always work on globally hyperbolic manifold from now on. Yes, so I will not repeat that again and again because this will make the slides very long. And, well, without surprise, the Cauchy problem for the Klein-Gordon equation on a globally hyperbolic manifold is well posed. What does that mean? It means if I take any Cauchy surface, and if I have a Cauchy surface, I will have on that Cauchy surface, for that Cauchy surface, some normal vector field. Yeah. On that Cauchy surface, I need initial data. This will be the value of the field, say, on that Cauchy surface and its first derivative. In this case, meaning the normal derivative of the function. And I will also allow for some source on the right-hand side of the Klein-Gordon equation. Then there is a unique solution to the Klein-Gordon equation such that Ku is equal to F, where the restriction of that solution to the Cauchy surface is this initial value, and where the restriction of the normal derivative of the solution is the other initial value. And this solution has a number of very nice properties. In particular, it has a special causal support property. Such a hyperbolic equation like the Klein-Gordon equation, it does not propagate its initial data outside of the light cone. Meaning, if I intersect, well, meaning that the solution will be in the causal shadow of the initial data and the source. And you see that here in this maybe very long and cryptic property that I wrote down here. The support of U intersected with the causal future, say, of the Cauchy surface. So let's now just look into the future of the Cauchy surface, is inside the causal future of the Cauchy data in the union with the causal future of the source, but only the source that is in the future of the Cauchy surface. So if I had another part of the source down here underneath the Cauchy surface, this wouldn't contribute to the support of the solution on top, over the beyond the Cauchy surface into the future. And it has also all the other nice properties, this solution, that you would expect. It's linearly dependent on the initial data and the source. It's kind of obvious, and it's also continuous in some reasonable sense. Now we have very special solutions. If you give me any
Daniel, there's a question.
Yes.
Here. Is it necessary that the initial data is compactly supported?
No, it makes it a lot easier though. So you would want, if you drop compactly supported and you don't go to the distributional side of the theory, you would need some other aspect. You need maybe that it's integrable over the Cauchy surface, say, something like that. But yeah.
Thanks. I think that's answered.
Something like that. Of course, if the Cauchy surface is compact, then just take. Then you're pretty. Then you have a nice, easy setup, let's say, and not much can go wrong. Yeah, certainly, if you're in the smooth case, you don't have anything to worry about. Right. But let's say we will always work with the compactly supported functions. Because essentially you don't need more. You can then just dualize, say, and look at distribution theory to handle the rest. Simplified. Anyway, later on we will also, since we always work with distributions, we always care about compactly supported functions. That's why I only work with this simple case here. I don't try to be as general as I can in this section. If I did, this would be almost impossible to understand in a short time, especially if you haven't seen it before. And I would need a lecture only for that. Anyway, so if I have now some compactly supported function, I can find a unique solution which is supported only in the causal future or causal past of that function, that source. And let's prove that. Essentially, we reduce it to the Cauchy problem that we already had. We choose a Cauchy surface. Sigma, and we want it in the past of F. So we want it such that the support of F is contained in the causal future of sigma. And to give us a bit of breathing room, let's remove sigma from that set. So the sigma is somehow up behind F, something like this. Then we can write down a Cauchy problem. Let's try to solve the Cauchy problem, which is K U plus is equal to F, and the initial data on that Cauchy surface are just 0. By the slide before, we know that this has a unique solution. And we also know something more. We know that this solution has a certain support property. We know that the support of U plus is contained in the causal future of the support of F. Because there is no initial data at all, we don't have to worry about the causal future or past of any of that. This gives us U plus, almost. We have to kind of bit worry about whether this solution that we now obtained depended on our choice of Cauchy surface. But it does not, because we saw that the solution that we obtained is 0 in the past of F, everywhere. So take now any Cauchy surface in the past of F. The restriction of that solution in the past to that Cauchy surface will of course be 0, and the same will be true for its normal derivative. So this solution does not depend on the choice of sigma. And of course, we can do the same with U minus. Now that we have these solutions, we can associate an operator to them. So there exists a unique linear operator called J plus and another unique linear operator called J minus. They are what's called the retarded for G plus and advanced for G minus green operator, such that if I apply G plus or G minus to a compactly supported function and then apply the Klein-Gordon operator to it, then this gives F. What does it mean? It means that this is a solution to the Klein-Gordon equation with source F. And obviously, this has the support property that I like. Namely, it's supported in the causal future, respectively in the past, of the support of F. If I did this in the other way, first apply the Klein-Gordon operator and then this green operator, then the same holds. So a bit briefer notation for the same thing, but one has to be a bit more careful with this notation, would be to say the composition of the Klein-Gordon operator with these green operators, whatever order do, is the identity. Also, they are the adjoints of each other, at least in some, when you restrict them to compactly supported functions. And I will show you in the proof now what exactly I mean by this. If you know more about functional analysis, you might be interested that in many cases these advanced and retarded green operators are not very nice operators, so you cannot expect them to be even closed operators. So we cannot really talk about vigorous adjoints or anything like that. So let's number these properties 1, 2, 3, and 4, and let's prove all of them. So to prove 1 and 2, and simply their existence as well, we don't have to do anything. We simply define G plus or G minus as the map which sends a compactly supported function to its future solution, as described by the lemma before. Yeah, and by the properties that we've already seen in the lemma before, we know that we get a solution for the inhomogeneous Klein-Gordon equation. So 1 is satisfied, and we know that the support property holds. To show 3, we use a trick. We define, well, we choose any function compactly supported, and we give this function also an alternative name. Let's call it also u. Then I can apply the Klein-Gordon operator to that function. Get ku. Obviously, ku, just by definition, is also equal to kf. But then, by the uniqueness of solutions to the for the advanced and retarded solution that I showed before, you get that when you apply G plus to kf, that this must be u, which is also equal to f. So you're done. For 4, we need to do some integrals. Let f1 and f2 be some compactly supported smooth functions. Then taking the integral of j minus the advanced green operator applied to f1, multiplied with f2, and now I omit the volume form. So this is the integral over the whole manifold, yes, with the appropriate volume form given by the metric. So maybe once, let me insert it. This is given by the metric density. Let's write it like this, or the volume form given by the metric, something like that. This is equal to, now I can insert one of these ones as I have them here. So I have G minus F1 and G plus, K G plus F2. Then I can do what is essentially just integration by parts and move the Klein-Gordon operator to the other side to get K G minus F1 G plus F2. But Kj minus is just the identity again. So this is F1 G plus F2. Actually, I forgot to say that the only reason I can do integration by parts so easily is that I used G minus and J plus here. Yes, I used that nothing kind of touches the boundary, namely the support of G minus F1 and the support intersected with the support of G plus F2 is compact. So I have no boundary terms from the integration by parts. There are no problems. Let's move on and take the difference now of the retarded and advanced propagator. And this I will call the Pauli-Jordan propagator, but a more prevalent name in this community is maybe Courset propagator. This is formally skew adjoint, meaning if I take the adjoint of this, in some formal sense, I get minus Pauli-Jordan. This is not surprising because if I take the adjoint of G plus, I get G minus, and so if I take the adjoint of G minus, I get G plus. So I have G minus, the adjoint of the Pauli-Jordan is then G minus minus G plus, which is exactly negative of what we started with. Since the retarded green operator has support to the future and the advanced has support to the past, taking their sum, we get in general something which has support in the future and in the past of the support of the function that we start with. And now this is a very condensed notation. We have a very useful property. We have that the following exact sequence, well, the following sequence is exact. And what does that mean? It means if I look first at this part of the sequence, let's call that 1. It means that the kernel of the Klein-Gordon operator, if I restrict the Klein-Gordon operator to the compactly supported smooth functions, is 0, just a set containing 0, and the range of the Klein-Gordon operator restricted to the compactly supported smooth functions is contained in the compactly supported smooth functions. So, well, if I take derivatives of a compactly supported smooth function and multiply it with something, it's still compactly supported and smooth. Now, next, look at the 3 spaces and 2 arrows in the middle. Then I find now the exactness tells me that the kernel of the Pauli-Jordan propagator is exactly equal to the range of the Klein-Gordon operator restricted to the compactly supported smooth function. So this means if I apply the Pauli-Jordan propagator to the Klein-Gordon operator applied to a compactly supported smooth function, this is 0. And if I have the range, take the range of the Pauli-Jordan propagator, this we know by this support property that if I apply the Pauli-Jordan propagator, the solution will be supported in the causal shadow of the function that we start with. So in particular, taking slices, we see again, this is space-like, compact. Now, sliced by any Cauchy surface gives me a compact well, gives me a compact function on that Cauchy surface. So we get something which is a space-like compact function. And now looking at the last three spaces, we find that the kernel of the Klein-Gordon operator restricted to the compactly supported, the space-like compact functions, this is equal to the range of the Pauli-Jordan propagator. And this is probably the most important property of them all. It means that all solutions which are space-like compact of the Klein-Gordon equation can be obtained by applying the Pauli-Jordan propagator to a compactly supported function. Mind you, this relationship is not one-to-one because the Pauli-Jordan propagator has a non-trivial kernel, which we have here. Yeah, and the last, maybe relatively irrelevant aspect is that the range of K restricted to the compact, the space-like compact functions is again space-like compact.
Daniel?
Yes.
A question. Can one further continue this exact sequence to the right?
Yes. But I don't want to talk about that. Maybe you have something to say about that, Chris. I don't know.
Well, I won't interrupt it. Yes, yes, you can indeed. And it continues exact and finishes there.
Yeah. Right. So using all of this that I just wrote down, you can define this space Q that I will use later today, probably again. So the quotient space of the compactly supported smooth functions by the range of the Pauli-Jordan propagator is equal, because the range of the Pauli-Jordan propagator is just the kernel of the the range of the Klein-Gordon operator is just the kernel of the Pauli-Jordan propagator. We have the first equality, and then this is isomorphic to the range of the Pauli-Jordan propagator just by standard theory. And the range of the Pauli-Jordan propagator is equal to the kernel of the Klein-Gordon operator. And the kernel of the Klein-Gordon operator, that's just a set of all homogeneous solutions of the Klein-Gordon equation. So when we talk about all the solutions of the Klein-Gordon equation, we can just as well talk about this space Q. But the advantage of the space Q is that we can talk about compactly supported functions. And they are much easier than some strange set of solutions.
Sorry, another question, Daniel.
Yes.
Is it a sequence of C infinity modules? Oh, sorry, I see that Alex Schenkel has... no, there's a... I beg your pardon. There are several conversations going on in the chat at one time, I think. Yeah. So let me just pose the question. Is this a sequence of C infinity modules, C naught infinity modules?
I wouldn't know what that is, so I cannot answer. Maybe Alex can.
I think it's not. We have in fact, there's a comment here because the multiplicative property is not very well.
Yeah, exactly. Differential operators are not module maps.
Yeah.
Then I continue. to another useful property. We call this the time slice property. And this is very much related to the fact that there is not a one-to-one correspondence between the compactly supported functions and the solutions. Namely, you can find that if you have a solution which satisfies the Klein-Gordon equation, and you take any two Cauchy surfaces, doesn't matter, then you can find a function which lies in between the two Cauchy surfaces, which you can use to generate that solution by applying the Pauli-Jordan propagator. Yes. So pick your two Cauchy surfaces. You have given your solution. Then you can always find a function, a compactly supported function in between these two Cauchy surfaces. And then U is equal to the Pauli-Jordan propagator applied to that compactly supported function. Let's also prove that. I cannot write anymore. Okay. We will choose now a function, a smooth function, let's call it He, on the manifold, and this will be a special function. We will choose it such that its values are between 0 and 1, such that its values in the future of sigma plus are 1. So here we have that it's 1. And in the past of sigma, it's 0. So here is 0. And in here, it's between 0 and 1. Okay, now introduce a new function, actually two. Let's introduce U plus, which is He times U. So this is something which is supported in the future of sigma. And introduce U minus, which we define as He minus 1 U. Now this is supported in the past of sigma prime. And if we, with these definitions, we can write also the function, the original solution U, simply as U plus minus U minus. Then the He part drops out and we have only this minus 1 U left over. If we now apply K to this equation, then Ku is 0. This can only be true if Ku plus is equal to Ku minus. Let's give that a name. And we will see that this is exactly the F that we are looking for. Clearly, we have that the support of F must be contained in the support of U plus, because Ku plus reduces at most the support of U, doesn't enlarge it, and it must also be in the support of U minus. So we take the intersection of the two. But as I said before, U plus and U minus, they are contained in the future of sigma, respectively in the past of sigma prime. So we know that this F that we found is now definitely in between these two Cauchy surfaces. We now only have to show that GPJ, the Pauli-Jordan propagator applied to F, is actually the solution that we started with. So let's choose some compactly supported function, which is arbitrary. Then we can make the following computation. Let's take the integral over the whole manifold of u plus multiplied with phi. This is equal to the integral of u plus, and now I plug in, again, similar to before, the identity, which is just the Klein-Gordon composed with the advanced green operator. Then I can use integration by parts, or if you want the formal self-adjointness of the Klein-Gordon operator, to move that to the u plus, but k u plus is just f. So I get this expression. Now I can also introduce a 1 in front of f. And use again the formal self-adjointness of the Klein-Gordon operator to get g plus f phi, because k with g minus gives me again the identity. Okay, so I have shown now that for all phi, u plus is equal to g plus f. So we get from this u plus is equal to g plus, so the retarded green operator f, because phi was arbitrary. We can do the same thing with u minus. And if we do this, we get that u minus is equal to g minus f. And hence, u, which is equal to u plus minus u minus, is equal to g plus minus g minus applied to f, which is just the Pauli-Jordan propagator applied to f. Okay, this is all I have about the Klein-Gordon operator. Let's take maybe now a break of 5 minutes and then continue with star algebras. I can answer questions in this. Okay, let's go and continue talking about star algebras. Without explaining you what a star algebra is, I will already say explain some principles that already include these terms. Sorry for that. I didn't think maybe about the right order of these things, but it will make some things. So the principle that is somehow behind algebraic quantum field theory and the motivation for this chapter is that we want to model physical systems by star algebras. And these star algebras are then typically called algebras of observables. Not all elements of these algebras of observables are necessarily equally important. Typically, we are interested in the self-adjoint elements, so those which are equal to their adjoint. They are called observables. We also need states. States are some functionals on this algebra with certain properties. They need to be positive and normalized, and this then relates to our standard probability interpretation that we have also in quantum mechanics. And then we can also make sense of saying something like taking expectation value of an observable. So the evaluation of that state on an observable, we interpret this as expectation value of that observable in some state. And well, we have a obvious example. We have quantum mechanics, where this is very much concretely realized, this principle. There we have a canonical commutation relations generated by the Cartesian coordinates or position operators and momenta. There's finitely many, so we have finite number of degrees of freedom. This has a essentially unique representation. Typically, we never talk about representations when we talk about quantum field theory. Okay, maybe you heard about Schrödinger picture and so on, but yeah. So maybe we want to talk about L2 of R, so on. We don't worry much about this. We can work in a fixed Hilbert space because there's an essentially unique representation, and the formulation of quantum mechanics is relatively simple. This changes a lot when we go over to quantum field theory. And this is because we have an infinite number of degrees of freedom there, essentially. While the algebra, so the algebraic relations between the observables have a very clear formulation. It's not so clear which Hilbert space one should work with. There's a large number of inequivalent representations, and they very much depend on the physical situation that you look at. So this is really something important. It's not just some mathematical aspect of the theory that is of no physical relevance. Yeah, so sometimes we can interpret this, for example, that in one representation, the other representation has, you get some mathematical problems because essentially between the two representations, there's an infinite number of particles, and so you cannot fit this into the mathematics. You have to choose then a different representation. Right, let's come to the definition of a star algebra. A star algebra is an algebra over the complex number, which has also an involution. That's so some way of taking adjoints of things. And so we have the standard properties that we need then. The sum, taking the adjoint of a sum is the sum of the adjoints. If we have a scalar, some complex number, we have to take the complex conjugate of that. If we take the adjoint of a product, we have to exchange the order. And if we take the adjoint twice, we get the original thing back. Often we want a bit more than just the involution. We want also a unit. If we have a unit, meaning that something which, the multiplicative unit, when multiplying with the unit from left or right, we get the original operator, then we call this star algebra unit. And there are some trivial examples. Standard examples are operators on Hilbert spaces. The easiest case maybe if you take the square matrices of some fixed dimension, and as your involution you take the conjugate transpose, then you have a star algebra. Slightly more complicated or exactly the same, depending on which dimension you're working in, are the bounded operators on a Hilbert space with the adjoint. The other thing that I needed in the principle were states. States, as I said, are some functionals on the algebra. So we want a linear map, which is positive and normalized. Linear, the first two properties. Positive, the third one. And normalized, the fourth one. If you have two states, you can take a convex combination of the two states. So say we have omega 1 and 1 minus lambda. omega 1 to get a new state omega. If we cannot write a state as a convex combination of distinct states, then it's called pure. Otherwise, it's a mixed state. And coming back to the example that we had on the previous slide, what is an obvious state if we are working with bounded operators? Well, think of quantum mechanics. You take a vector in the Hilbert space, and this induces a state by just taking the inner product with the A applied to psi and taking the inner product with psi. So this is a vector state induced by a vector. Of course, more general states would be obtained by density matrices, maybe so on. Now, maybe there's a theme already. Like before, we had globally hyperbolic manifolds. Then we talked about maps between two globally hyperbolic manifolds. Now we talked about star algebras. Now we need maps between two star algebras. A map between two star algebras is, well, let's say, nice. Again, it's a star homomorphism, meaning if I apply it to a sum, it decomposes nicely. I can pull out scalars. It behaves nicely with the adjoint. So the adjoint or the involution of one is mapped to the involution of the other algebra. And if also the one, the unit, is mapped to the unit, then we call this star homomorphism unit preserving. Also here, we can look at an example. Let's consider the space of square integral functions. Here, let's now not take the bounded operators as a star algebra, but for each interval of the real line, we can form a star algebra of multiplication operators. These are just the functions. If you start with a function psi in L2 of R, then mu, where u is some essentially bounded function applied to psi, is just u times psi, which is still square integral. And there's a natural star homomorphism between any two such algebras simply by extending or restricting these functions, extending them in whatever way you like, by constant or by zero. Well, the natural one would be by extending by zero, I guess. So this, in quite a bit more complicated way, will be our way of will be the algebras that we look at later. There we will also have star homomorphisms, which kind of also relate to maps where we restrict functions. No, sorry, where we not restrict, where we extend function. Right. I don't want to talk about representations, but I probably should a little bit because many people are used to working with Hilbert spaces, and representations are very interesting and rich subject. But I will not give the proper technical definition, but essentially a star representation or representation of a star algebra is a very particular star homomorphism of the star algebra into a Hilbert space. well, actually into the operators of the Hilbert, on the Hilbert space. And rough example would be the star algebra generated by the position and momentum operators with their canonical commutation relation, which can be represented on the square integral functions by the usual multiplication by x or differentiation. Yes. And importantly, once we have a star algebra and a state, we are given a representation kind of for free. Yes. So star algebra plus state is equivalent to working on a Hilbert space. And if you don't need all the power of theory on Hilbert spaces, you don't need to go to the Hilbert space representations. And we mostly won't, or we will not need it, so we will not go there. We will work with the algebraic formulation only. This finishes the section on star algebras, and we can continue to the algebraic formulation of quantum field theory. Especially, or really, for the scalar field on curved spacetime kind of optimized representation here. So at the foundation of quantum field theory, or sometimes one also say the quantum field theory is an assignment of a globally hyperbolic spacetime, or for any globally hyperbolic spacetime, no, to any globally hyperbolic spacetime, we associate a unital star algebra. And to any admissible embedding between two globally hyperbolic spacetimes, we assign a unit-preserving star homomorphism between these star algebras. And we want that this assignment satisfies some nice properties. We want that it's covariant, meaning if I compose two embeddings of spacetime, then the associated maps between the algebras should also compose in the obvious way. Yes, so whether I do the algebra homomorphism in one step or in two steps shouldn't matter. The theory should be causal, meaning if I map, well, let's say I have two n1 and n2 and map them into a larger spacetime, then if they are causally disjoint, now it didn't fit quite like that, but let's make this like this, so it looks more causally disjoint. Then the algebras associated to these small regions mapped into the large region should commute. All elements of these algebras. This is causality. Observables in different regions, this just says that observables in different regions of the spacetimes, if they are causally disjoint, do not, cannot interfere with each other. Is there a reason for having star algebras? I will come to that in a second. Also, the spacetime should be the assignment should be dynamic, so there's some form of dynamics. Meaning, if I have a region which contains a Cauchy surface, yeah, so this is really a spatial slab of the spacetime. This contains all the information. All the measurements I can do in that slab can be related to measurements that I can do in the whole space-time, simply by, let's say, Cauchy, by solving the Cauchy problem. Yeah? So there's some dynamical law which propagates observables through the space-time. And if you know a bit about category theory, you might have noticed that this looks like a functor between a category of globally hyperbolic spacetimes with admissible embeddings as morphisms into the category of unital star algebras with unit-preserving star homomorphisms as morphisms. And the covariance of this functor is then essentially, but not only, given by this covariance requirement that I have here, and these other properties, well, they are addition.
Daniel, there's a follow-up question. Is there a reason for restricting to embeddings as the arrows between spacetimes?
Well, how would you extend? You would somehow have to make something up. So I guess that answers that. And concerning star algebras and not C-star algebras, well, star algebras certainly contain the topic of C-star algebras. So I want to be a bit more general. And in particular, the example that I will have later will not be a C-star algebra. Many things are maybe easier and are mathematically nicer with C-star algebras, but yeah.
I have another question. Why do you consider unital star algebra? Because globally hyperbolic spacetime is supposed to be non-compact manifold.
I want a unital star algebra, otherwise I cannot make sense of the statement that the state is normalized.
Okay. But then how do you, will it not be in conflict with your non-compact manifold like globally hyperbolic spacetime?
No.
Because what we know that unital star algebra is an algebraic version of a compact manifold kind of. It's compact, topologically compact space.
I think the confusion here is that the algebras that Daniel's talking about are not just algebras of functions on the manifold. Okay, if they were, then what you say about the compactness and unital would be correct. But these are not just algebras of functions.
Okay. Then, with this principle set up, let me continue to talk about the example that we're interested in, the scalar field. Let me introduce the polynomial canonical commutations relations algebra of the scalar field, or simply called the field algebra or the algebra of smeared quantum fields. This is the unital star algebra, which is generated by smeared fields, which we just think of at the moment as some symbols. These are some symbols which are labeled by compactly supported functions. And this is the algebra which is generated by these, subject to these symbols satisfying some linearity property. The adjoint is given by complex conjugation of functions. The commutator of two fields is given by the Pauli-Jordan propagator. Maybe you remember, hopefully you do, that the Pauli-Jordan propagator is skew joint. Yeah, so if I moved the Pauli-Jordan propagator from the G2 to the F1, then I would get a minus sign. So this makes this all compatible. And if you know quantum field theory with equal time commutation relations, then this is actually just equivalent to this, but I have no time to show this right now. And the last property is that the field should be the solution of the Klein-Gordon equation in the distributional sense. Meaning, if we have the relation that associates 0 to the symbol labeled with the Klein-Gordon operator applied to some compactly supported function. And that's the star algebra or the field algebra for the Klein-Gordon field. So this is relatively straightforward, but maybe not terribly concrete. Some other comments maybe that also relate to the C-star algebra question is this algebra cannot be represented by bounded operators. So maybe it makes it technically, for some cases, more difficult to work with. If you want to do that, you can work with the Weil algebra, which is a C-star algebra, but which I will not discuss here. And the reason why this cannot be represented by bounded operators is just the same as when you talk about the position and momentum operators. You cannot represent operators which satisfy commutation relations of the type here by bounded operators. The other problem, if you want to call it a problem, of this algebra is that you cannot have squares of fields. But when you think about quantization, saying you want to quantize the stress energy tensor, or even more, if you want to talk about interacting fields, using maybe perturbation theory, you want to be able to take powers of fields. You cannot do this here. This type of elements are not in the algebra. So you need a better algebra for that. And maybe a more concrete algebra, but equivalent to this one, and one which allows for better generalization, is the next. So if you think a bit about it, the algebra that we just constructed looks very similar to a symmetric or bosonic Fock space, just that we're not working with Hilbert spaces here. So we have the direct sum over symmetric tensor products of this space QM that we had before. And the space QM, if you remember, this was just the space which was equivalent to the space of solutions of the Klein-Gordon equation. And this vector space we now equip with a more, well, with the appropriate algebra product, and we can give this recursively in this way, that in each step we remove one of these stars and to produce one symmetric tensor product, and pairing pairing Fn, which I take out here, with each of the other factors in the product, and producing a commutator essentially, so or half a commutator. So we get a Pauli-Jordan propagator. This is kind of like a Wick's theorem, just not with Feynman propagators. So this is really the same type of formula that you have there. you have kind of contractions, but with Pauli-Jordan propagators. And this phi, I forgot to say, this is just the projection into the first component of this type of Fock space. And as before, we have involution defined by complex conjugation. Now this space, or sorry, this algebra has the advantage that we can relatively easily exchange the product by something more suitable maybe for what we need. And indeed, if we replace the Pauli-Jordan propagator here by something somewhat nice, and I won't go into details, you can allow for the construction of Wick polynomials. And the problem of constructing Wick polynomials is, in this algebra is essentially that you cannot take powers of the Pauli-Jordan propagator in some sense. Yeah, distribution theory will not allow you to do that. The singularities don't match up nicely.
Daniel, there's a question. Can't we specialize to the case of abstract unital C-star algebra as the algebra of observables in curved space-time, and then it would be bounded under representation? But
yes, well, this is what I meant with my comment about the Weyl-CC algebra. So certainly we can, going all the way back to this principle, we can work with C-star algebras instead. Then, in my example, we can not write down the polynomial CCR algebra, but the Weyl-CCR algebra. In a sense, we just take the complex exponent of the fields, at least heuristically, and get then the appropriate relations between these exponents and get a nice C-star algebra. But for many applications, it's more direct, at least, to work with the star algebras. It's at this step, I agree, it seems better to work with C-star algebras. But already when you talk about this deformation type, well, this star product approach to this algebra, and then going over to Wick polynomials, you will have more problems with the C-star algebraic approach. And other things come less natural. So it's better to work with star algebras, in my opinion. Now I said, but I will not prove it, these two algebras are the same. And both of them, kind of because they are the same, they satisfy the properties that I wanted in my principle. They are covariant, causal, and dynamic. But for this, of course, we need to choose the appropriate maps. And namely, what we associate to every space-time embedding, which is admissible, we associate a star homomorphism, which is given by the push forward. Yes. So we just push forward functions, or actually, okay, these I have quotient space. And then after we pushed forward the function, we extend the function, the compactly supported function, by 0. Yeah. Yeah, so you have your space-time n, you have some compactly supported function in it, you have your bigger space-time m, in which you embed n, and then you push forward that function in here. It's still compact inside that set, and you extend it by 0 to the whole spacetime. Okay, now covariance. So this is a sketch of a partial proof. Covariance then simply follows by the fact that if we have two admissible embeddings, call them chi and psi, then their push forward is equal to the composition of the push forwards. If we have causality, because if we have two functions compactly supported, which are causally disjoint, so, or rather more precise, causally disjoint support, then the Pauli-Jordan propagator applied to them is 0. Because, if we remember, this is defined as this, but the support of F1 intersected with the support of the Pauli-Jordan propagator applied to F2 is contained in the support of F1 intersected with the causal future of the support of F2 and the causal future, causal past of the support of F2. But because they are causally disjoint, this is empty. So this must be 0. And dynamics, this last property, that follows from the time slice property. Yeah. So the notes will eventually contain some more details, which I'm not ready to present here in the last few minutes. Instead, I want to introduce the concept of endpoint function. If I have now a state on my polynomial CCR algebra, I can apply the state to a product of fields. And to any product of n fields, I can now call this the endpoint function. This is simply a distribution. Yeah? And typically, this is written really as a function of n points of the manifold, rather non-rigorously. And because our algebra has the properties that we requested from it, for example, this commutator, if I exchange two arguments in the endpoint function to have them in the other order, I get a correction term, which is given by the commutator. And if I plug in a compactly supported function together with the Klein-Gordon operator, then what I get is 0. In other words, these endpoint functions are weak solutions, so distributional solutions of the Klein-Gordon equation in every argument. There's a special set of states. for which only the 2-point functions are really important. And to make the definition of these states, let us first look at a certain set of graphs. We look at the set of directed graphs with labels from 1 to n, where each vertex, as in this example that I drew there, is met by exactly one edge. And they are ordered in such a way that the source has a smaller label than the target. Exactly. This is, I mean, this is really just the set of ordered pairs, right? Oh. And then a state will be called quasi-free or also Gaussian if we can write its even endpoint functions as products of 2-point functions. We simply sum over all possible ordered pairings. So we get a long sum of products of n half 2-point functions. And the odd endpoint functions all vanish. Then actually, another way of saying this, if you're familiar with the term, is quasi-free states. For quasi-free states, all the truncated endpoint functions vanish. And one thing that makes quasi-free states so very interesting is that they have a Fock representation, which is what we are typically used to from representations for free quantum field theories. So this was kind of the way of going from a state to an endpoint function, or specifically a 2-point function. Also go the other way around. We take a 2-point function which has certain properties. This will induce a state. The state should be positive. Broken down to the level of simply 2 factors of fields, we would need that this is positive, but that's just the same as the left. We also want the commutator relation to hold, which is the second condition. And we want that the 2-point function is a solution of the Klein-Gordon equation. And actually, because of this commutator relation, it's okay. It suffices to look at only one of the arguments. The other one is then for free. And then we can define all higher endpoint functions by taking products of the 2-point functions. And once we have all the endpoint functions, the state is uniquely defined. And if you have a state, you can calculate its endpoint function. In particular, you can calculate the 2-point function of the state. You can throw away all the other endpoint functions, thereby liberate the state to get a quasi-free state, and determined only by this 2-point function. Okay, so let me finish with some remarks. We've seen how to construct the field algebra for the free scalar field, and this was relatively straightforward. I mean, once we've learned about star algebras and so on, I mean, it's not trivial, but it's relatively straightforward. What's absolutely non-trivial is the construction of good states. Maybe you can find some relatively trivial states, which quite easily, but constructing states on curved spacetimes is a very non-trivial matter, and there's a lot of literature on this. We have constructed this field algebra, but starting from there, we can also construct more general algebras, which contain more general elements that we might want, like big polynomials. And to do this, as I briefly mentioned, you essentially have to modify this star product. Not all states are relevant, really. And especially when you go to this extended algebra. I mean, if you extend the algebra, then the set of states becomes smaller, because the set of states is the dual, or a certain part of the dual. One has to think what should be the condition for a physically relevant and mathematically well-behaved state. And essentially, this is the topic of the last two lectures by Matteo. Because a good class of states are the Hadamard states, and they have some very nice properties which make them both physically and mathematically desirable. It's not enough to work with just one particular state. The state must fit the physical situation that you're looking at. If you work with a different state, it will typically have a different and inequivalent representation. As long as you restrict yourself to the Hadamard states, the representations are somewhat similar. They are so-called locally quasi-equivalent, but I will not go into that. And one might wonder whether, like in quantum field theory, on Minkowski spacetime, there's something like a vacuum in curved spacetime. And the answer should be a resounding no. There is no such simple preferred state. At most, if you have spacetimes which are asymptotically stationary, you have something like in and out states. This is probably the best you can do. And all attempts to find distinguished states on a general curved spacetime are probably as pointless as trying to find a distinguished coordinate system on a curved spacetime. Yeah, that's it. And it's 5.
Perfect timing. Thank you very much indeed, Daniel. I guess you'd be available for a few questions if people are still keen to ask. And in the meantime, let's thank Daniel.
Yeah.
I can clap. Other people might put a sign. Very good.